Yeah. Uh, Good afternoon, students. Today we will discuss the another important topic from our module 2 or chapter 2, that is partial differential. Today we are going to discuss the concept of exact differential, what exact differential means, how it is useful, and what are the other implications of that. Now, this first slide shows you we write this total differential of any given function f is a function of f of x and y. These are the two independent variables. This is dependent variable. Its total differential is calculated as, or is written as, df is equal to partial differentiation of f with respect to x, that is fx, into dx, and plus partial differentiation of y with respect to partial differentiation of f with respect to y, keeping x constant, that we call it to be fy, and then this is multiplied by dy. Now let's write this to be df is equal to m dx plus n dy, assuming that this fx is a function of x and y again, as well as fy to be also a function of x and y again. So I'm writing this f of xy, fx is another function of x and y. Similarly, this fy is also a function of x and y. Now I'm calling this to be m and this to be n. Further, we have to differentiate this m with respect to y and differentiate this fx, or that n, with respect to x. So this type of mixed differentiation or cross multiplication differentiation. So get differential of m with respect to y and get differential of n with respect to x. This is as good as earlier we have seen this condition, delta square f upon delta x into delta y is equal to delta square f upon delta y into delta x. So this second order partial differentiation already we have seen. So using this concept here, let me write this. So we are not coming. Sorry. Yeah. So this second order cross multiplication I'm writing this to be yeah. So this differentiation of here it is delta y into delta x, and we have already seen generally the second order mixed derivatives are equal. So what happens if they are equal and what happens if they are not equal, that is this particular derivation is. So get differential of m with respect to y, so that is nothing but delta square f upon delta y into delta x, and this is delta square n upon delta x into, sorry, this is delta square f upon delta x into delta y, because n itself is delta f upon delta y. So this is a mixed second order partial derivatives, and if they are equal, then the given df is said to be an exact differential. This is called as an exact differential, okay, provided this condition is satisfied here. So we are supposed to use this condition for further, okay. So now let us go for some simple problems example based upon this definition of this exact differential, that will be in the second. So please check. Now this is the example you have been given. Df is equal to df of xy is equal to 3x square y minus 6y square xy square plus y cube into dx plus x cube minus 6x square y plus 3xy square into dy for an exact differential. For that we have to compare. So this is nothing but m and m of xy, and this is nothing but n of xy. Now, so comparing this, I get this is m, this is n. So for an exact differential, we have to write this differential equation in the form df is equal to m dx plus n dy, and now differentiate this m part with respect to y, differentiate n part or n function with respect to x, and show that whether they are equal or not. If it is equal, then such type of differential is said to be an exact differential. Now let's go for actual solution of this. So that gives you solution here. So d of of xy is equal to 3x square y minus 6y xy square plus y cube into dx plus x cube minus 6x square y plus 3xy square into dy. So m dx plus n dy can be written. So m is this 3x square y minus 6xy square plus y cube and y cube, and n is equal to x cube minus 6x square y plus 3xy square. Now this is what m and n. Now differentiation of m with respect to y. So it is del by y of 3x square y minus 6xy square plus y cube. So all these three terms are now functions of y. So differentiate 3x square y with respect to y, you get 3x square. Differential of 6xy square with respect to y is 2 into 6 is 12x into y, then plus 3y square. Differential of that will be y cube is 3y square, so we'll get 3x square minus 12xy plus 3y square. That is your equation 1. Similarly, get differential of this second, that is delta n upon delta x. So here differential of x cube with respect to x is 3x square. Differential of 6x square y is, again this comes to be twice x, so 6 into twice x into y plus 3y square. So using this, that again gives you 3x square minus 12xy plus 3y square. That is my equation number 2. So 1 and 2, both these equations are exactly identical, having three terms and having same form, and therefore this condition delta m upon delta y is equal to delta n upon delta x is satisfied, and this is what we have seen to be a necessary and sufficient condition for a df to be an exact or not. In this case, this given df is an exact differential, and whenever an exact differential is there, that given function f can be computed using this integration method. Actually we are not doing it here, but try to understand. That is this. Another example, d of x y is equal to 3x square y minus 6x into dx plus x square plus twice y into dy. Here this is nothing but m and this is nothing but n. So again differentiate this m with respect to y and n with respect to x, and let's check what is there. So m is 3x square y minus 6x, n is equal to x square plus 2y. Differential of m with respect to y gives you 3 delta by delta y of 3x square y minus 6x. Here only y is the 3x square y, that first term is a function of y, so it remains 3x square. Similarly, the second differential delta n upon delta x of delta x square y plus 2y upon delta x. So that gives you here a differential of only first term x square, so that comes to be twice x. So delta n upon delta x is equal to twice y. This doesn't satisfy the condition, so this condition delta m upon delta y is equal to delta n upon delta y is not satisfied. Hence this df is not an exact differential, not an exact differential. Okay, now if it is the case, then we can show here this f cannot be calculated. Okay, so here we have shown these two examples to be, one is exact differential, one is not exact differential, and what I want to show here is that this particular exact differential format is very useful in thermodynamics. How? In thermodynamics we have two different types of functions. So one is called as state function and second is called as the path dependent function. Not only in thermodynamics but other branches of physics also dependent function. Now for example, this is what I am drawing one graph here. So this is one state and this is the second state. So here it is P1 T1, this is first state, and P2 T2, this is the second state. So thermodynamic state, pressure 1 and temperature 1 is this A state, and this is B state, that is the temperature, another state of that thermodynamic system where pressure is P2 and temperature is T2. Now to bring the gas, okay, gaseous system from this to this, there are several ways. One is this way, this is second way, this is third way, and there can be any other way like this. So there can be several ways for going from state 1 to state 2 or state A to state B. Now state functions are that going from A to B, state functions are dependent upon okay, initial and final state only. Okay, so therefore, for example, entropy. Entropy is a function of pressure and temperature. Then if I get its differential of this entropy, its partial differential will be this: df is equal to delta S upon delta P, keeping temperature constant, into dP, plus differential of delta S with respect to T, keeping pressure constant, into dT. This equation will be an exact differential equation. This equation will be an exact differential equation. This means this is my m, this is as good as n. So differentiate this m with respect to temperature, so delta m upon delta T, and differentiate this with respect to this n with respect to P. This is what nothing but one of the Maxwell's equation. So Maxwell's equation is this. Okay, sorry, just a minute. All four Maxwell's equations are obtained this way. So this is what an entropy. So entropy is a state function. It depends only upon initial and final state. So whatever way may be used, you'll find that entropy is a dependent upon only initial and final function. So in that is a state function. Whereas there can be some other functions. Actually, I am not naming this function. So this some function is like h, which is again function of pressure and temperature. And if I found out its total differential, dH is equal to exactly the similar way, delta H upon delta P at constant temperature into dP, plus delta H upon delta T at constant pressure into dt. Here also, if I calculate this be m, call this be m, and this will be n, differentiate m with respect to t, and differentiate this n with respect to p. If they are not found to be same, they are different, then h or dh will not be exact, will not be an exact differential, and therefore this h, corresponding h, is path dependent. So this concept of path independent and path dependent functions, that can be understood from this exact differential. So that is the actual application of this exact differential in thermodynamics in mathematics. So and one more very important statement I would like to make here: when a given differential equation is the exact differential, such function is state dependent, and that can be calculated by making this integration and all that methods. Whereas if this type of condition is not satisfied, the given differential is not an exact differential, hence such type of functions cannot be determined. So whether function is determinable or non-determinable, that will be decided by this type of differentials, whether it is exact differential or not exact differential. If it is exact differential, then it is determinable. If it is non-exact, if it is not an exact differential, then it is non-determinable. So that is to be understood from this particular concept of exact differential. Okay, thank you for